Okay, so we have a problem here we want to solve today, and the problem is the following. Evaluate the limit by recognizing the sum, which is in the limit, we're going to write in a second, as a Riemann sum for a function defined on the interval 0, 1, and the limit is this limit for n that goes to infinity of the sum with I that goes from 1 to n of 5i cubed divided by 3n to the power 4. Alright, so let's do a little bit of a discussion, try to understand what we're going to do. So the important fact to point out is that the limit of a Riemann sum is by definition the definite integral. So the limit for n that goes to infinity of the sum with I that goes from 1 to n of f evaluated at the point xi times dx is by definition the integral between a and b of a function, the same function f dx, and this is the Riemann sum. So the limit of the Riemann sum is the definite integral. In addition to that, the delta x, the interval that we get in the Riemann sum, is related to the boundaries of the interval of the integral by this expression, and the xi are defined as a plus I delta x. Alright, so the point is that if a limit can be written as the limit of a Riemann sum, then the limit can be rewritten as a definite integral. So in this case, solving the definite integral will be equivalent to solving the limit. Sometimes solving a definite integral is easier than solving the limit itself, and that's why it is sometimes useful to rewrite the limit as a definite integral. So let's go over the solution. How do we solve this? Well, the first thing we need to do, we need to prove that our limit, which I'm going to rewrite here briefly, is a Riemann sum, which is defined as the limit for n that goes to infinity of the sum with I that goes from 1 to n of a certain function f evaluated at the point xi times delta x. Now, before we go any further, let's factor out that number 5 over 3. It doesn't really do anything. It's just a multiplicative factor. So to simplify our lives, let's take it out of the limit. And now let's figure out, let's look at the Riemann sum and let's calculate delta x in our case. So delta x is defined as b minus a over n, and remember that our function is defined over an interval 0, 1. So that means that a is 0 and b is 1. So with that in mind, delta x is going to be 1 minus 0 over n, or simply 1 over n. So let's evidence this factor here. because it's going to be useful later. So delta x is 1 over n in our specific example. Okay, let's calculate now the xi's. This is defined as a plus I delta x. So a is 0 and delta x is 1 over n. So the xi is simply I over n. Okay, let's evidence this result as well. Alright, so now with this in mind, we can rewrite our limit 5/3 limit for n that goes to infinity of the sum for I that goes from 1 to n I cubed over n to the 4th as 5/3 limit for n that goes to infinity of the sum I that goes from 1 to n of I over n cubed times 1 over n. See, the argument of the sum is still I cubed divided by n fourth. Alright, but 1 over n here is delta x, and I over n is xi. So our limit can be rewritten now as a Riemann sum, which is what we wanted to do when we started, as 5/3 limit for n that goes to infinity of the sum for I that goes from 1 to n of xi cubed times delta x, because delta x is 1 over n and xi is I over n. But the limit of a Riemann sum, and this is the limit of the Riemann sum, is the definite integral between 0 and 1 of x cubed in dx in this specific example. So now we can calculate that integral, which is fairly simple, and this is going to be 5/3 times x4 over 4 evaluated between 0 and 1. That's 5/3 times 1 to the 4th divided by 4 minus 0 to the 4th over 4, which is simply 5/3 times 1 over 4, or 5/12. So this is the result of the integral, but because the integral is basically our limit, we can say that the limit, our original limit, which is the limit for n that goes to infinity, sum I goes from 1 to n, 5i cubed over 3 and 4th is 5/12. And with that we can conclude.